Good afternoon, everybody. Last time we stopped solving a problem of three-phase Y source, Y load. We did that and found out that it's really easy just to solve it using equivalent circuit, using single-phase equivalent circuit, just one line, because both are Y. What happens if you have one side not Y connected, not star connected as delta? Very simple. There are many ways to solve it, but just choose the simplest way. If you have delta load like that and balance, and we are dealing only with balanced load in this section. So all what's supposed to do, find the equivalent Y. Example, if they have this 130 ohm, and you want to find the equivalent Y would be like that. That's equivalent Y. You connect the load at the points here. Each one will be one third of the impedance. So if this impedance 30 ohm, so you divide it by 3, you have 10 ohm, 10 ohm, 10 ohm. And you go ahead and continue use the same method when we solve Y connected load. And then find the equivalent single phase circuit and just do it in the same way that we did. So no problem. If you have delta, just convert it to Y. If you read the textbook, there are other methods you can read it if you like, but I mean, I prefer that. I prefer to have just one method and stick to it and understand well. So that's the way it's solved. Now let's just talk about the power in a three-phase. To calculate the power, and then when I say power, it means active power, reactive power, complex power, all types of power. You can use single phase and you can use line-to-line quantities. If you are using phase-to-phase or using phase quantity to calculate the power, that's okay. Calculate the power, reactive power, complex power in single phase and then multiply it by 3. If you like to deal with it. If you want to use the line-to-line quantities, you can do it directly by multiplying square root of 3. That's the only difference, simply. Let's just go into some detail. So the first one here is the complex power, S. It will be root 3 multiplied by the line voltage and line current and the angle theta. The angle theta, there is nothing called the angle of line or the angle of phase. All angles per phase. Nothing called angle of line. If you want to use the phase quantity, so the phase voltage times the phase current times 3. That's the only difference. Using phase, multiply by 3. Using line quantities, root 3, square root of 3. Somebody might ask, does it make difference if it was delta or star? No, doesn't matter. And remember, theta, it is the angle difference between the angle of the voltage and the angle of the current. Let's take just an example. We want to determine the average power. When we say average power, it has different names. Real power, active power, the watt. The active power, bars, and the complex power at the source and the load. That's the source, obviously here. So that's the source. And that's the load. And between the source and the load, like in the same example we did last lecture, but we're calculating the current and the voltage across the load. So how can you find, first, I mean, to calculate the power, first you have to find the current, because as you know, the way to calculate the power is using complex power, S. So how can you calculate that? You find the single phase equivalent. That's one way to do it. So you have one impedance, 5 minus J2 ohm, and you have one load, all Y, so it's easy, 10 plus J8 ohm. And you have the source. You take, for example, phase A, or using phase A, 110 and angle 0 voltage. Let's now just try to find the power at the load term here. That's the load. And we need to find the power. So it's better to use the complex power. That's one thing. So how you write the complex power? If you are using phase, I'm doing phase now. If you are doing the phase, so you have 3, the voltage phase, I phase, and the angle theta, where theta is the difference between theta V minus theta I. So that's, I mean, the general rule for complex power. That's the voltage across the load in phase, because that's the neutral, and the current is the same current, because in series, that's I phase. Yes. Minus, that's 8 plus J8, and that's 5 minus J2. Three V phase, I phase, and the angle theta. That's one? Yeah. No, I mean, because I can do bold in bold. So I just make line to, because there's difference between S bold and S not bold. S as a vector, it's a complex power. S magnitude, if only you're looking for the magnitude, like 3 times V phase times I phase, it would be the apparent power. So there are difference between S bold, but I can do it bold. So I just make line to say it's a vector. It's not scalar magnitude. It's not only magnitude. The only magnitude of this part has different name, apparent power. That's why I'm doing this. Some people use different thing. They don't put anything there, and the apparent power they write like that. Means the magnitude. So we might use that. So that's the apparent power. And this the complex part. So let's just calculate. We need to find the current and the phase. So I will add the all impedance in the circuit. So I will say Z total will equal to Z of transmission line, 5 minus J2 plus the impedance of the load, which is equal to 10 plus J8. So 5 plus 10 is equal to 15, and the imaginary part minus J2 plus J8 will be plus J6. And that will be the impedance in ohm. Now I want to find the current. So I just divide, I would say I phase is equal the voltage of the source divided by the total impedance. And the voltage of the source also is phase. I'm picking the phase one. So that will be 110 on angle 0 divided by the total impedance, 15 plus J6. And just use your calculator. I'll just calculator on complex mode. 2, and then I will say 110 divided by, open bracket, 15 plus 6i. Right, I got it in a complex form. I will make it an Euler, like magnitude and an angle. So I'll just again use my calculator. 3, and that's what I got. 6.8, and the angle -20. I mean, you can do it with your calculator. Maybe I will do a mistake or something. And that's the current phase. I got I phase. I need to find the voltage across the load. The voltage across the load, V phase, I can multiply the current by the impedance of the load. So I can write equal I phase times ZL. That's ZL. So in this case, I phase, I have it 6.8 and the angle -21.8. And the impedance, you can leave everything as it is and just multiply in the calculator. You don't have to worry about it. And you get the voltage. Point 8 times 10 plus 8. And I got 87. And I'm rounding the answer. 16.9. That's voltage. So you got the voltage and you got the current. How can you find the complex power that will give you everything? Give you the active power, reactive power. I will use this formula. Just to find phase, the power in one single phase, you say the voltage times the current conjugate. That's for one phase. You want to find three phase? Multiply by 3. That's it. Just adding 3 because I'm using phase quantities. So according to what I have here, I have 3 times V phase, which is equal 6. Oh no, it's not. That's the current. That's the voltage. 87 angle 16.9 times the current conjugate. So that's the current. I'm going to use the conjugate by changing the sign of the current. That's the conjugate of the current. Now it's easy. I'll multiply. When you multiply the magnitude, I'd like to multiply first the magnitude to be 3 times 87 times 6.8. That will be equal to 1774.8. And this is the magnitude, and this is the apparent power. S magnitude. The angle, I'm going to add both. 16.9 plus 21.8. I got 38.7. That's the complex power. That's very important. You want to find the active power, reactive power in the calculator, just convert this form to complex, Cartesian form, real plus imaginary. So I will just do that. Of course, you can say that the power is equal, the apparent power, 1774.8 times cosine 38.7. That's the power, active power. Reactive power be the same magnitude, 1774.8 times sine 38.7. Can do that too. But just the way I'm just going to do the calculator, that's all. Doesn't cost anything. 1774.8 at the angle. 38.7. And just give me everything in converted automatically. 138.5.1 plus J 110 1109.7. Okay, just one the calculator. So the real part will be the power, active power. Imaginary part will be the active power. Done. Let's say that they ask about the power factor of the load, only of the load. So I will say that the power factor, I can divide it the power magnitude by the parent power magnitude. So I have 1385.1 divided by the magnitude of S, 1774.8, and I get the power factor. Just very simple. Or we can do it by cosine the angle. What is the angle we're going to use? This angle, 38.7. And you can check it by yourself. You get the same answer. So you have many ways. It's better to do it in many ways. So that's the way that you're going to solve it. We have it. Why connect it like that? Do you have any question on this problem? Okay.
Excuse me.
Yes.
One question.
Yes.
Because we had that more complicated circuit in the beginning, and then we simplified it into this smaller circuit, kind of like a square right here. I didn't know. So that was just for the 8 days?
Only for the 8 days.
Okay.
That's right.
And then you connect the neutral and the ground.
Yes. You also had a question problem on your chat earlier, by the way.
Which number what?
On the screen, the Zoom screen.
Oh, somebody asked. Oh, okay. Let's see. Okay. Thank you for that. What slide I didn't. Oh, I'm going to upload them in the PDF for file. Not only just the recorded, I will save it as PDF. So you don't have to worry too much about that. Just write the notes for yourself, things that you think it's important for you to forget. But everything will be on the file. And then just I share it to my Google Drive and then download it. Okay. Okay. Let's look at another way the problem is given. A balanced three-phase load receives 15 kilowatt at a power factor 0.8 lagging when the line voltage is 48 volts root mean square. Represent this load as a balanced Y connected load. It's a very practical problem because I mean when you graduate and then you work with power, then just I mean everything is given like that's the power and this is the power factor and this is the voltage rated voltage, and then you can figure out to get the other parameters. So it's a very normal practice. So you see, I mean the problem here is like 1.5 lines or 2 lines, but it's good one because it's practical. So we'll say that is the load. I have load. I mean, he wanted the end to be like balance Y load connect, but let's just represent this as 3-phase load. And I just put the information, the power, and the power 15 kilowatt, not phase. That's for the 3-phase. So that's equal 15 kilowatt. And the power factor is equal to 0.8 lagging. And the voltage, line voltage. So I have to write VL is equal to 480 voltage root mean square. By the way, all equations I used in previous example, it's assumed that the values in root mean square, that the voltage 110 was root mean square. So you have to pay attention to that. The all equations based on root mean square values. So that's, I mean, root mean square, all right? And the angle of the voltage is not given. We always assume it angle 0, the reference, doesn't hurt. Now we want to represent this load. So it's a Y. So we want to find Z for the load. Of course, there is nothing called line impedance, always impedance per phase. So how we tackle this problem? There is a relationship between the impedance and the voltage and the current. Any impedance, like if when you tackle this problem, just you look, I mean, okay, I want to find Z, so what I need, what the information I need to get Z. To get any Z, you cannot get Z per line, as we said, per phase. So you have to know the voltage per phase across the impedance and the current flowing through the impedance. So I say I need to know the voltage phase is phase across the impedance, and I need to know the current phase. And since it was assumed that the load was Y connected, so in this case, you have to remember that the line current is equal phase current in star connect or Y connect. So now my goal, I want to find the voltage on the current. How can you find the voltage on the current phase? You have the power, you have the power factor. Okay, the great thing, as I told you, it's like a magic formula. I mean, when I was a student, I thought that's the magic formula. Complex power is great because complex power relates the whole power terms with the voltage on the current. So it almost solved everything. So I will say S equal to, since the information given in line quantities, I'm not going to use the one I used in the previous example. I'm going to use the equation that deals with line-to-line quantities. So I'll say equal square root of 3 V line, I line, all right, and angle theta. That would be the formula I'm going to use. And S here is complex power. Do I have the VL? Yes, I do. So VL is equal to 480. So it's equal to 480. The current in the line is not given. All right. Theta is given in a way. Power factor is given in a way. It's given 0.8. And I know if I have the triangle of the power and I have S, P, Q, that's theta. And I know power factor is equal cosine theta. So we know that power factor is equal cosine theta. So cosine theta is equal 0.8. Why did I draw Q upward? Because it's lagging power factor. What about it was leading? I make Q downwards. All right. So now I can find theta. Theta will be equal to cosine minus 1.8. So I will do that and we'll see the angle now. That's shift cosine 0.8. I get 36.87 degree. Okay, just make it simple. Fine. That's the theta. I got theta, so I plug in the equation here. S is given? No, it's not given. Power is given. Well, can you get S if you know the power and power factor? Yes, I know. There's a relationship between power and S. Here the triangle, power triangle. We know that P over S is equal power factor, right? So I can find S. S is equal power time S equal power divided by power factor. So just let's write in here in space. So S, the complex, the apparent power is equal to power, which is equal to 15 kilowatt divided by the power factor is equal 0.8. So I have 15,000 divided by 0.8. So I have 18750. But this is the apparent power, right? I only got the magnitude because I didn't know the direction of the current. So this is the apparent power. So the apparent power is equal 18,750 volt amp. That's S. You go back to the equation. Where is your S magnitude? This one. Because the complex power, when you write it as a vector, the complex power is equal the S magnitude and angle. The difference between complex power and apparent power is just the angle. So I got the magnitude. So I know this magnitude is equal to 18,750 volts amp. So is it going to help me in something? Yes. It will help me to get what? the line current. Because in this formula, I'm missing the current. So I will say the apparent power S, I have it here in the equation, the magnitude, that's √3 times 480 times IL. It should be equal to 18,750 volt amp. From this equation, I can get the current, the line current, right? So I'll say the line current will be IL will be equal to 18,750 divided by square root 3, 480. That will give 22.56, and you can check if I did it right or wrong. That's the current. Now you go back to the problem and check what we need. We need to find the impedance. To find the impedance, we need two things: the phase voltage, the phase current. And since the load is Y connected, the phase current equal to line current. So now I can write I phase equal to I line equal 22.56. Is it right? Not completely right, because current has magnitude and an angle. Has magnitude and angle. And if you write like that, it's not right. So what is the angle of the current? Well, go back to this equation. We assume that the voltage on angle 0, which is acceptable. It's okay, you can assume it any angle, which is 0. So, and we know theta, it's the difference between the voltage angle and the current angle. And we got it, 36.9. So I know that theta is equal to 36.9 is equal the angle of the voltage minus the angle of the current. I know the angle of the voltage is equal 0. We assume it. It was not given, I used as a reference. Minus theta I should be equal 36.9. Now we can say that theta I is equal to negative 36.9. Now we have the current expressed in the right way. You have to remember voltage, current in sinusoidal has a magnitude and an angle. So now I can say that the current phase, which is equal to the line current, I just have it here, but was missing the theta I. So it's equal to 22.56, and the angle is equal negative 36.9. That's the current. Do I know the phase? Yes, I know the phase. It was given. The phase was given line voltage equal 480 and the angle is 0. So let me write that. The voltage, that's equal to 480, angle 0. I need the phase. And this is Y connected load. Now we got to know what is the relationship between the voltage, line voltage and phase voltage in star connected. If you go back to the table, you'll find that in Y connected load or source, the magnitude of the voltage line to line is bigger than the phase by √3. If you remember, let me remind you, the line to line voltage in star load, the line voltage is equal √3 times the phase, right? It's the only thing. If there is anything else, what is the relationship between the line voltage and the phase voltage in a star? The magnitude we talk about it. It's √3. What about the angle? there is a shift of angle. If you forget it, but you should have your paper that has the all. But if I forget, I never remember. So I'll say that's the, if this is the phase, I'll just remind you. If this is the phase we did lecture before, VA, VB, VC, the phase, and you want to find the line VEB. VEB would be VA minus VB. So I just flip VB, that's the minus VB, and then I complete the parallelogram, and we found this 30, and this VEB. So we know that the relationship between the phase voltage and the line voltage, 30 degrees. I'm interested in the phase. So the phase, you look at the phase here, it's smaller. So it means I divide the line magnitude by square root of 3. And the angle will be lagging by 30 degrees. Obviously here. And I always drive it. I used to drive it, but I mean, drive the equation, but you have it in the formula that was given. It's given for you. I mean, the lecture before, between the relationship between the line and the phase voltage, it's 30 degree in Y connected. So I can say now that the phase voltage is equal the line voltage divided by √3, smaller. This one is bigger. And whatever the angle you have for the voltage, you just subtract 30 because the phase is behind the line voltage. It's below. So it means lagging. We know that the theta of the voltage of the line, it was given 0, which we choose as reference 0, right? Okay. So I will say the line voltage was 480 divided by square root of 3, and the angle was 0 minus 30 voltage. I will do that in the calculator, then we'll find the magnitude, 480 divided by square root of 3, that's equal to 77. I just round the number, minus 30. That's the phase voltage across the load. That's the phase voltage. Now we already defined the impedance. We have the voltage, we have the current. That's the voltage, and that's the current. And very important, don't just focus on the magnitude. We are not working in DC circuit, it's AC. So everything vector has a magnitude and an angle. Now I can say the impedance of the load per phase equal to the voltage divided by current. And the voltage is equal to 277, and the angle is negative 30, and the current 22.56, and the angle is negative 36.9. I will do that. 277 divided by 22.56. The magnitude give 12.28, and the angle that will go on the top, that would be 36.9 minus 30, it will give 6.9 ohm. Always convert this to Cartesian complex form. So I will say that's 12.28, and the angle is equal to 6.9 positive. I get the answer 12.2 plus J 1.47. Oh, that 8 ohm. So the load consists of resistance in series with inductor. The resistance is equal to 12.2 ohm, and the reactance of the inductor or the inductive reactance equal to 1.48 ohm. That will be that. So you look at the problem, it's only 1.5 lines, but there is a lot of work involved in it. It just, if you understand this problem, I think you will be good in analyzing three-phase circuit and also single-phase circuit, because it's just, it's going from one point to another, but you got to follow up why you're doing the step, why you're doing the step all the time. And this is not the only way to solve the problem. I'm using different method for solving this problem. Intentionally, like, I mean, I'm taking with you step by step, see how you think, you want to get this one, how you get this one, like that. But there are different ways to do that. Like, I mean, at least 4 methods. So do you have question in this one? Yes.
Do you want us to wait until the end to change, so if you have negative phase angle, do you want us to wait till the end, change to a positive phase angle?
Are you talking about this part?
Right.
Yeah, when you are dividing, you divide the numbers, you get this one, and the angle when you get something from the bottom to the top, you change the sign. Or if you want to get something from the top to the bottom, you change the sign. You always change the sign. Yes, when you change its place. Any question there? That's an important topic that we need to discuss it now, that how to correct the power factor. And that's a very practical situation. You have that's the line and the load. Maybe you have 1 load, 2 load, 3 load, whatever, that's the combined load connected to the 3-phase system. And let's say you calculate the power factor of this combined load, then you find it's low power factor. It's not good. It's like 0.7, something like that, 0.8, and you need to bring it to 0.94 at least. So how you do that? You connect capacitor in parallel with the load. To do that, just let me sketch the power triangle. I will remind you, if you have the power of the combined load here, that's the power of the load, and that's the reactive power of the load, and that's the apparent power of the load, and that's theta, and the power factor is not good. When you add a capacitor in parallel, so the Q of C it go in the opposite direction. So it go like that, subtracted. So you'll find in the end, you can reduce QL, the whole thing, only to this quantity. And when you reduce QL, the power and the S will be close to each other as magnitude. It makes the power factor better. It's improved. So always our goal is to find the reactive power of the capacitor. What's the required reactive power that the capacitor need to deliver to the system to improve the power factor? I have problem here, but just, I mean, the problem is involved, but I like, I mean, to give you, like, before this example, I'd like to explain it a little bit in simple way. So let's say that, you know, your system, the power, reactive power, something like that. You have system and it take 100 kilowatt. And you have, of course, usually they don't tell you what is the reactive power of the load. It tell you about the power factor. Let's say power factor was given as, or the angle here was given like 45 degrees. So in this case, the power factor will be cosine 45 degrees. That's equal to 0.707 lag. And if you want to find Q, you can find Q for the system, for the load. How you find Q? Using the trick, you can get the Q here, because Q over P power is equal 10 theta. And you know theta is equal 45. And 10 45 is equal 1, right? So Q is equal also 100 kilovar. So it's not a good power factor. to improve it, let's say that you want to make the power factor 0.9. 0.9. So let's say the new power factor, you make it power factor dash, star, whatever, is equal to, you want a 0.9. You want a 0.95 lagging. That's the new one. So you got to ask yourself, okay, what is the corresponding angle? The new angle. We have new angle. What do you expect? The angle will be bigger than 45 or smaller than 45? Smaller. Because the best situation, the ideal situation, theta is equal to 0. When theta equals 0, the all S is consumed as active power. But practical 195. So what's the corresponding angle? Theta dash. Because you have the old theta is equal 45. I can do it arc cosine 0.95. The angle is now is equal 18.2 degrees, of course less. So now you have a new value for Q, because theta, the new theta here, that's the theta dash, the 18.2. So that's the Q, the new Q. So how can you get rid of all this to reduce Q, the original Q, to the new Q, the small one? So how you can get rid of it? You add capacitor, deliver this quantity, the difference. So the difference here, that's supplied by the capacitor. Because the capacitor is obviously the inductor. The inductor consumed the inductive power, but this one delivered. So I'll say delta Q is equal the old Q minus the new Q, and you can get the Q by using trig. Once you get delta Q, we said this is going to be done by the capacitor C. Done by the capacitor C. How can you find the value of C or XC at least? How we can find XC? Well, we know that Q can be found by V squared over X. So if you are looking for Q delivered by C, it's V squared divided by X. C. So if you know the QC, and I know QC, that's the old Q, that's the new Q, when you subtract, that's QC. And the voltage is the voltage of the system and the load. If the load taken 120 volt, it's the same thing on the capacitor, because you connect the capacitor parallel. Then you can find XC. Let me give you now one problem, and we have 8 minutes left. It's a 5-minute problem, like exactly what I explained. See how did you understand? You have a load, and just to make it simple, I'm talking about single phase. I want you first to understand the concept. So you have a load, and the power is equal to 50 kilowatt. Q, I'll give you Q also. I mean, to make it simple, to save your time. Q is equal to 50 kilovar. The voltage, 120 voltage across. The question is, find XC to make power factor is equal to 0.98 lag. I want to find XC. Just exactly what I explained now. 20 months.